Hi guys, sorry about all the technology problems that we were having tonight. Where we had left off is we were talking about two very common logarithms that are actually on your calculator. We can see this on my screen right now that I have the Desmos Scientific Calculator up, and the two logarithms that they actually have, the functions are on here at the bottom. I'm pointing to them. One is just simply a log. Log by itself has a base of 10, so the base 10 is our common one. So if I put in log of 10, we're going to get an answer back of 1 because 10 is our base raised to the first power is equal to 10. 10 to the second power would be equal to 100. So if I take log of 100, I'll use the function key, put in parentheses. So if I take log of 100, I'm going to get an answer back of 2. Log of 1000 would be equal to 3 because 10 raised to the third power is 1000. Okay, so log of 10,000, which was in the example, should be equal to 4, and so on and so forth. So every base 10, every time I multiply by another 10, that's going to give me another exponent. So 10 to the fourth power is 10,000, and so on and so forth. So a logarithm without a base is a common log, and that just means the common log is always base 10. Okay? The other one we were talking about is what's called a natural log. A natural log is something that occurs a lot in finance. If you're curious to find out a little bit something more about ln, so if I want to take ln of 100, well, that's not going to make a lot of sense because we got 4.605. It goes on forever and ever. This is actually base E, and I'm going to show you what that is real quick. E, if I push up E, actually E comes up as a number. It's not a variable. E is a number approximately 2.718, and so on and so forth. Now, where did this number occur? Now, I'm not going to get into the specifics of E. If you want to wish to find out more about the origins of E and how we use it in finance, I dropped a video in the content resources about the introduction to the number E. So E by itself is about 2.718. So if I take E and raise it to the power that I got before, which is 4.605 E, and there's my 100. So that's the work backwards. So E raised to the 4.605 power is equal to 100. That means the natural log of 100 is equal to the 4.605, and so on and so forth. You can see how they are inverses of one another. So the most common logs are log of base 10 and logs of base E, which is called the natural log. Now, what do we do in situations in which we don't have a base 10 or we don't have a base E? Well, we'll talk about how we can rewrite all of our logarithms to be a base 10 or to be a base E so that we can always use the part of the calculator. Okay, so two most common logs are the base 10 logs. That's called your common log. So if I see just a log of x, that means log base 10 of x. If I see this is not a 1, this is an L. ln stands for natural log. I don't know why they don't make it NL. That would make too much sense to make it NL for natural log, but it's ln. That just means it's log base E of x. And so that's what we're going to be able to use for our other things. So when we're rewriting these ones up here at the top, if I want to write a logarithm that's in natural log and back into an exponent, remember this is going to be log of base E. So log base E of A is equal to negative 16. That means E to the negative 16th power is equal to A. E to the negative 16th power is equal to A. Okay, the one down here, the logarithm by itself without a base, remember I can put a little 10 in there to make it base 10. That means 10 to the fourth power is equal to 10,000. That's how we can rewrite logarithms as an exponential function. Down here we had started to write some, I'm going to have you guys can do that on your own. Okay, so I will fill in a couple of these so you can see them. And then I will make sure that this gets posted with the answers in them as well. So I'll just go ahead and put the answers in, and then you can try them on your own to make sure you got these. 2. There we go. So that's rewriting all those exponentials as logs. Down here, we're going to use our change of base formula to teach you how to evaluate logarithms. So this is how we are going to set this up. Again, this is not in your textbook. Your textbook is going to show you how to evaluate logs using the methods that we used on Wednesday. But of course, that method is only good for so many kinds of problems. We're going to show you how to do it in general using the change of base formula. So if x is equal to log base a of b, then I can simply change a base a to a base 10 or a base e, and then use my calculator to evaluate. That means x is equal to log base 10 of b over log base 10 of a, or just log b over log a. So the base, which is a, goes on the bottom, base for b, base for bottom. So a goes on the bottom, and the log of b goes on top. Or I can use natural log of b over the natural log of a. So how do we evaluate log 2 of 64? Well, this was actually in the video. This means that 2 raised to some power is equal to 64. Well, 2 to the 6th power is equal to 64. So log 2 of 64 would be equal to 6. Now, the way we learned it on Wednesday was to take 2 to the x power is equal to changing the 64 to a base 2. That would be 2 to the 6th. And then I could set the exponents equal to each other. That would be a base 6. Okay, so that's how we would use this if you don't have access to a calculator with a base 10. But since you guys all have access to a calculator with base 10, we're going to show you how to find log 2 of 64 is equal to 6 by using our change of base. Okay. Come on, you're going to erase for me? You're not going to erase for me. Nope, I guess not. So we'll just have to keep it with that. Okay, so how else are we going to get 6? We're going to change our base to a base 10. That means we're going to write this as log 64 over log 2. Or you can use natural log of 64 over the natural log of 2. And that will still get us an answer of 6. So we'll go in and we'll use this in our calculator. And we'll just use this as simply log 64 divided by log 2. You can see that we get an answer of 6. I can also use my natural log, which is a key down there, natural log of 64, divided by natural log of 2. And that will also give me the answer of 6. Because 2 raised to the 6th power is equal to 64. And that's our reverse. So that's an exponential and that's a logarithm. So we use logarithms to help locate or help find exponents. Okay. So the same thing over here. Remember, the base goes on the bottom, so log 125 goes on the bottom, and log 5 on top. So log 5 over log 125. So I can do log 5 divided by log 125, and that equals to 0.333333, or 1/3. 1/3. And the reason why that works is because 125 raised to the 1/3 power is equal to 5. Remember, 1/3 power is the same as a cube root. So the cube root of 125 is equal to 5, because 5 raised to the 3rd power is equal to 125. That's why we get the answer of 1/3. And again, you can still use natural logs for that too. Natural log of 5 divided by the natural log of 125. And that's 0.333, which is the same as 1/3. Okay? So we can do that for all of them. So what I'll do is I'll just put in, you can just put in the change of basis, and then you can use your calculator to go back and evaluate them. Okay. So I'm not going to spend too much time on that. You guys can do that on your own, evaluating each expression. So once again, log 125 over 5, or you got log base 4 of 164. Remember, you can rewrite this again. I want to be able to evaluate this. So log 1 over 64 all over log 4. And that way I can use a base 10 to evaluate that one. So just be careful, put that in parentheses. That means 4 raised to some power is equal to 1 over 64, and that's what you want to find. Okay? Cool. All right. And we can do that for all of them. This would be log 5 over log 125. Well, I think we just did that one. I don't know why we're doing it again. It's all right. It's all good. We can do it as many times as we want. Okay? Let's see. Log 36. Again, you could probably do this one in your head. You probably don't. Again, for the ones that you can do in your head, like 6 to what power is equal to 36? That would be 6 squared. So log base 6 of 36 would be equal to 2. Because 6 squared is equal to 36. So I didn't even need to use my change of base formula for some of these, if you know what they are off the top of your head. Okay? Cool. And that's how we can evaluate using are rewritten, or you can just simply use the change of base rule. All right, next thing we're going to do is we're going to learn how to learn how to solve logarithmic equations. That means if we have a logarithm with a variable in it, we're going to solve these by changing them all to exponential form. And that's our approach. So if I want to solve for these, I can solve for the exponential. So the first thing I'm going to do is I'm going to just simply rewrite this. So I'm going to rewrite this as an exponential. Log base 5 of x is equal to 2. Now remember, 5 is my base. The logarithm is always set equal to the exponent. So that's the same as 5 squared is equal to x. Well, 5 squared is equal to 25. So if 25 is equal to x, that means that x is equal to 25. Remember, solving for a variable just means I want to find out what's the value of x. What's the value of x? Sometimes we might have an expression in there. If you have an expression, that's okay. For this one, I can just isolate the expression. And I can say that 3x plus 5 is equal to base 2, exponent 4. Base of the log is the base of our power. The logarithm is always set equal to the exponent. So this would be 3x plus 5 is equal to 2 to the 4th power. 2 to the 4th power. Well, 2 to the 4th power is equal to 16. So now I just simply have a linear equation where 3x plus 5 is equal to 16. Again, if you need a calculator, evaluate 2 to the 4th power. You can just go and you can find 2 to the 4th power. 2 to the 4th power. And again, you can see that you're going to set equal to 16. Okay, so 2 to the 4th power equals 16. So now I can just simply subtract 5 from both sides. And then divide by 3. So in this case, x is equal to 11 over 3. And that's it.